let's, without further ado, here we go. We'll get started with the short course in astronomy. Feel free to take notes during it, but I think this one is one where you probably won't need to take that many notes because things are of a general nature, and when they're specific, they're pretty well written down in the book. Okay, our place in the universe. Most people have no clue of our place in the universe. They know that I am me and I'm standing here, and I go outside and look up into the sky, and there are a bunch of dots of light up there that weird people called astronomers like to study. And we like to try to clarify that a little bit and just see how we fit into the overall scheme of things. We don't get into the teleology of it, like why are we here? We just set up the idea of where we are, and you can draw your own conclusions and think about why we're here and what we might be doing. This course is not based on a lot of memory work, although yes, there is a test at the end if you would like to get a certificate saying that you're a knowledgeable amateur astronomer. That's entirely optional, but it does not feature factual information nearly as much as understanding and concepts. However, like learning to read, before you can get into great literature, you have to at least learn the alphabet and learn how to read sentences. So we have a few things that are worth looking into to start with. And for sizes, let's just limit it to 3 things in the solar system. Our own Earth, 8,000 miles in diameter. That was determined a long time ago, and it's been about the same ever since. The largest planet in the solar system is about an order of magnitude greater than that. That would be 80,000. It's really more like 87,000, but just roughly a factor of 10 bigger for the largest planet, Jupiter. And then roughly 10 times that diameter again for the Sun, the star around which all the planets in the solar system revolve. So factors of 10, 8,000, 80,000, 800,000, give or take a few, and you can see there is a give or take of a few, but that puts you in the right ballpark of understanding the size of things in our solar system. Distances to a few of these things. The Moon, our nearest neighbor in space, 250,000 miles away. The Sun, nearly 400 times that far away, 93 million miles, just under 100 million miles away. Neptune, now the most distant planet. In fact, it was for most of the time, even when Pluto was a planet, because Pluto was in such a catawampus orbit that part of the time it was closer to the Sun than Neptune. So Neptune is probably all along should have been the last planet, and it's the most distant one, about 2.8 billion miles from the Sun, which is a fur piece, actually. That's out at the fringes of our solar system. Then, if we go past that, we have lots and lots of virtually empty space before we come to any other stars at all. The nearest one farther away from our solar system is Alpha Centauri, which is 25, you know how to count this off, 1,000, million, billion, trillion, at least in America. England does it a little differently. But 25 trillion, or 2.5 times 10 to the 13th miles away, which you can see is many orders of magnitude greater than the size of our own solar system. So our solar system is a speck surrounded by other specks at a tremendous distance. Okay. Those of you who are old like me, and I don't actually see that many people who are as old as I am, will remember the moon landings, the first one of which was in 1969. There were communications between the mission control on Earth and the astronauts on the moon. And they would say, how are things going? And then they'd be, doom, doom, doom. Oh, okay, up here. How are things down there? And then bloom, bloom, bloom. And then the answer would come back. It wasn't that we picked slow-witted astronauts by any means. It's just that radio communications between the Earth and the moon, our nearest neighbor, take about 1.3 seconds each way before the beam of light or radio waves can go from the Earth to the moon or from the moon to the Earth. So when you go out later this evening and take a look at the moon, you're not really seeing it as it is right then. You're seeing it as it was about 1.3 seconds earlier, because the speed of light, which is incredibly high, 186,000 miles per second. If we could travel that fast, we could go around the Earth 7 times in 1 second. Yet the distance to the moon is such that it takes longer than that, 1.3 seconds. Galileo was one of the first who tried to determine the speed of light, and he ultimately failed. He had lanterns set up on opposite mountains and tried to get friends to open theirs when they saw his and back again. And after a very frustrating evening, he pronounced that the speed of light was exceedingly fast, if not instantaneous. So that was the conclusion that he came to. Yet, at that tremendous speed, even our nearest neighbor has a lag. The sun, 93 million miles away, its light takes 8.3 minutes to reach us. So if it were to go out, which it won't, it would take us 8.3 minutes, or in the case of Memphis, maybe 2 weeks, to discover that the sun had gone out. Neptune, when you look at Neptune, and we almost did at the last observing session, but there was a nice little anvil-shaped cloud bank just right over where it was that didn't ever go away. In fact, it expanded and eventually overwhelmed us by the end of the evening. We would be seeing it as it was 4.2 hours ago, because at the distance of 2.8 billion miles, it takes its light 4.2 hours to reach us. And then Alpha Centauri, 4.3 years for its light to reach us. I've seen that star. You can't see it from Memphis. You can see it from southern Florida, and it's, you know, way up high in the sky in Australia, where I saw it from. And you're seeing it 4.3 years ago, as it was then. This leads to one of the most important definitions in astronomy, and that is the concept of the light year. Light year is a measure of distance. The term year in there might be misleading, and it might lead you to believe it's a measure of time. But that's sort of like saying how many grapes are there in a grapefruit. It's a whole different set of units. A light year is the distance that light travels in 1 year. And it's fairly easy to figure that out. If we start out with the speed of light at 186,000 miles per second, multiply 60 seconds in a minute, 60 minutes an hour, 24 hours a day, 365 days in a year. Notice how the units cancel. The seconds, the minutes, the hours, and the days cancel, and we wind up how many miles light goes in a year. And that comes out to be just under 6 trillion miles, 5.87 trillion miles in 1 light year. Okay, does anybody have any question about that, or any of the times and distances and things so far? Because this is a fundamental building block on proceeding. And note here, there's no star that close. Remember, Alpha Centauri was 4.3 light years away. We said in the previous slide that it took 4.3 years for its light to reach us. That means it's about 25 trillion miles away, or 4.3 times that distance. And that's the nearest of the other stars to our own solar system. So any question about that? Yes?
I just have a general question. All those images you mentioned in the earlier slide,
Mm-hmm.
one thing that always confused me,
Mm-hmm.
from, I guess, from my own reading and from a few readings,
Mm-hmm.
I know the universe is expanding.
Mm-hmm.
So I've always had trouble with that. Those differences really still
Yes. The universe being expanding applies on a grand scale to the separation between galaxies of billions of light years and so on. Within our solar system, we're not really in on that expansion, because it's we're such a small part of it that any expansion taking place is not reflected in our, and besides, we'll see what caused that expansion. You're getting to the last talk in the course about a year from now, but we'll see at that point what started all that expansion, and it doesn't involve the solar system. That started before there was a solar system. Okay, it was a good question, but we've actually thought of putting that in because it is a good question. Okay, Our galaxy, the Milky Way. A galaxy is a big spiral pinwheel-shaped group of stars. We live in one of them, and the ancients called it the Via Lactea, at least the Romans did, the Milky Way or Milky Path across the sky, because that's what it looks like on a clear, dark night. And we actually had one at our last observing session. You could see the Milky Way running pretty much from one horizon to the other. It's a band of light that corresponds to the outline of our galaxy from our position. The galaxy is huge. Our Milky Way is about 100,000 of these light years across. What did we go from 4.3 was the last figure you got from me. Now we're talking about 100,000 light years from one side of our galaxy to the other. So if there was a star here shining and it does something unusual, people on the other side of the galaxy, if there were any, would find out about it 100,000 years later, because it takes the light that long to go across our galaxy. 100,000 light years. We are about a third of the way in from one edge of the galaxy. It's kind of a lens-shaped object, and it's about 10,000 light years thick through the center, 100,000 across. It's about a 10-to-1 ratio approximately. There are other details which we'll get into later on, but for now that's a general picture. Here's another one, a face-on picture, and this has about 100,000 stars in it. Don't try to count them right now, but I think Bill drew in 100,000 stars in his drawing. Is that right? And again, we're about a third of the way in from the edge. And we can see a concentration of stars towards the middle and thinner out towards the edges. The spiral structure, as we'll see later on, is related to the rotation of the galaxy, but it's, again, not as simple as you think. So it's nothing turned out to be quite the way it looks in astronomy. There are always evolutions in our understanding of things. And we'll give you the latest stuff, but not all tonight. Okay, here's an artist's conception of the Milky Way galaxy. It probably has a kind of a bar through the center, and the spiral arms circle out from around that, and we can picture ourselves as being maybe about here, a third of the way in from an edge, inside one of the spiral arms. And you can see all kinds of details in here, dark clouds of gas and dust, bright pink glowing areas where new stars are forming. We'll see a little bit more about that tonight even. But this is a drawing of our galaxy. We don't have photographs of our whole galaxy. I showed this to a friend of mine, and he asked if this picture on here was the Milky Way. And, well, you know, that's not a dumb question if you don't know what the Milky Way is like and where we are in it. Because since we're inside it, we can't really see the whole thing. It's sort of like if you're locked in your house, you don't ever have a picture of your house. You can feel around inside and look around and take pictures and get some idea of what your house might look like on the outside, especially if you look out through the windows and see other houses up and down your street. They're not all the same, but you get some kind of idea of what a house looks like, but not exactly the details of your own. So we have to have many means of determining the size and shape of the Milky Way galaxy, and we'll get into those in due course, like this course. Okay, what's inside our galaxy? Well, of course, there's stars, one of which is our sun. A question, yes?
I have a question. We said that if something happens at one end of the galaxy and light takes 100,000 years and
right.
To be seen at the other end. But let's just say that the whole thing is being bounded by because of the mass together. So if something has to go away, wouldn't we feel those gravity effects instantaneously? We wouldn't know why.
No, it's not instantaneous either. Gravity waves, to the extent that we know anything about them, would travel at the speed of light the same. So if you have an instance, like for example, merging two neutron stars, which is getting ahead of where we are now. But if that happened, it would send out a gravitational pulse that would propagate at that same speed and take that long to get anywhere. Nothing is instantaneous as far as we know at all. It always has to propagate in some way. Okay. About 100 billion stars in the galaxy. Huh? Okay, all right.
Yeah, you said that our galaxy is expanding.
No, I didn't. I said the galaxies, the distances between them are expanding. But actually, even our nearby neighbors are not moving away from us, some are moving towards us. But again, that's like 11 months from now. So if you can hang on to then, it'll make a lot more sense. Okay. Okay. 100 billion stars. Here we are again, 100 billion stars. Give or take a few. No one has ever counted them. You have to just kind of do estimates on things like that. Many of them are double and multiple, actually. When I first got interested in astronomy 57 years ago, daring astronomers predicted that maybe as many as a third of all stars were double and multiple. Now it's probably more like 2/3, and many of the rest of those have planets around them. So the idea of a single isolated star, while theoretically possible, seems to be less and less a likely choice for what stars are. So they're generally, and many of them that you can see through even a small telescope are double and multiple. Many of the stars in the familiar constellations are double. Alpha Centauri is a double star. I forgot that till I saw it. It looked like two yellow cat's eyes looking back at me through the eyepiece. And Castor in Gemini is 6 stars in that system. So that's the rule rather than the exception now. There are gas clouds, nebulae. Nebula is the Latin word for cloud, and they abound in galaxies. They're made of gas and dust, and they can either be new stars forming from them, or they can be remnants of old stars, or a mixture of those, and we'll get into that as well. Several types of nebulae. There are clusters of stars. As it turns out, all stars are formed in clusters. You don't have just a single star forming by itself. They're always formed in groups or clusters. The ones in the plane of our galaxy, in the disk that we saw a picture of a little while ago, these are called open clusters. They're also, unfortunately, called galactic clusters. That kind of leads you to think we're talking about clusters of galaxies. But galactic clusters is the correct term for these, or open clusters. A cluster of galaxies is theoretically known as a cluster of galaxies. So you won't get that mixed up when we get to clusters of galaxies later on. Dozens to hundreds of stars, irregular pattern. We'll look at some pictures of those. And they're very numerous, and they're found right in the plane of the rotating galaxy. Globular star clusters are much fewer. There are only about 100 of them around the Milky Way, but they contain a lot of stars, anywhere from 100,000 to 1,000,000 stars in a compact ball-shaped arrangement, hence the term globular. And they surround the nucleus of the galaxy and sort of orbit in and out of the plane of the galaxy. They're not circling around in the plane like the open or galactic clusters are. We'll see a picture of one of those coming up as well. And here's something fairly recent. There's probably a halo of about 100 trillion red dwarf, very faint stars surrounding the galaxy. We'll see why they think that later on. You can't see them, but a lot of things you can't see, you can deduce that they're there, and we'll see why later on that we think the Milky Way galaxy has a halo of faint stars around it. Not this, this. Okay. Now I said we can't take a picture of the Milky Way because we're inside it, but we can try. This is a picture from inside the Milky Way, obviously, because that's where all astronomers are located. And this runs from the constellation Cygnus up here down through Scorpius and Sagittarius, when we're looking in towards the middle of the galaxy, and on down to constellation Carina that you see in the southern hemisphere. But you can almost imagine that this is the edge-on picture of the galaxy that we saw earlier, because when we're inside it, we are looking at it kind of edge-on. Imagine yourself as being a little ladybug on the spoke of a bicycle wheel, about a third of the way in from the wheel towards the hub. And you're riding around on this spoke on the wheel, and you can look all the way around, and all the way around you will be the outline of the wheel. And there's more material in that wheel in towards the center, in towards the hub of the wheel, or the hub of the galaxy in this case. It looks brighter there. If you look out towards the outer edge, things are sparser. If you look perpendicular to the wheel, there's just a few other spokes nearby, and that's about it. So the rest of the sky is rather sparse in stars compared to what you see looking right along the plane of the galaxy. Is that reasonably clear, considering we can't really have a picture of what it looks like from the outside, that we're inside looking all the way around? We've got some more pictures coming up of what it looks like at different times of the year later on. Here's some interesting things about stars. Some of which have been known for a long time, others are fairly new. Stars have different colors. How many of you knew that stars come in different colors? Well, that's good. You already know that they don't look like a string of Christmas lights. They're not intense colors, but rather pastel tints or hues of color. And the different colors indicate the temperature of a star. In fact, the color of any glowing object indicates its temperature. The coolest stars are reddish in color, and cool is a relative term there. I've got it in quotation marks. You wouldn't want to grab hold of it any more than a red glowing briquette in your barbecue grill. They're about the same temperature, hot enough to glow red, but and relatively cool compared to other things, but you wouldn't want to grab hold of it. A couple of examples: Antares and Scorpius, Betelgeuse in the constellation Orion in the shoulder of the giant. Those of you who picked up a sky map, you'll see Betelgeuse in the shoulder of Orion. It's a red supergiant star. Orange ones, a little hotter, a little greater in temperature. Arcturus is one such star. Aldebaran, I thought I'd put that on this one. Aldebaran and Taurus is another orange star. The yellow ones are intermediate temperature, sort of like a candle flame. And our sun is one such. Capella, the she-goat in the constellation Auriga in the northeast on your map, that's one of the yellow stars. We start getting a little hotter, we get to a white-hot star like Sirius in Canis Major, the brightest star in the sky, easily visible out in the southeast in the early evenings this time of year. People call me all the time when they see it for the first time. I'm not sure why it's the first time, but they see it and they call me, and they think it's a UFO of some kind, because when it's low in the sky, it's so bright that it's light going through the Earth's atmosphere. It makes it twinkle and shimmer and change colors, and it looks exactly like a classic UFO, except it's right there in the same place every night. So and it's white hot, somewhat hotter than the sun. We get to hotter ones still, blue, like a acetylene welding torch. And good examples of that would be Rigel in the heel of Orion at the south end of the constellation, or Spica in the constellation Virgo. Those are blue hot stars, among the hottest. There are a few violet ones, which are actually the hottest ones, but those are few and far between. There's some in the Orion Nebula, but there are not any bright ones in the constellations that are actually violet. So that's the color range of stars. We get to the sizes of stars. They're not all the same. They're certainly not the little dots that they look like in the sky. That
relates to the age of it?
indirectly. Now, you can't always say that a red one is old or new or something. A blue one is fairly young because they don't last very long. You do know that. So it's like rock musicians. They use up or athletes, they use up what they've got right away. So if you find an old one, that's extremely rare. So the blue ones are generally fairly young, but as we'll see later on when we get to the life story of stars, they go through a series of where they may actually change from one to another. And so the age is not directly related, but it's part of the story. It's a good question, but can't really answer it tonight. We have a little more background to go through first. The red supergiants are the biggest ones, like Antares and Scorpius or Betelgeuse and Orion. Those are hundreds of millions of miles in diameter, hundreds of millions. Bigger than the orbit of the Earth, bigger than the orbit of Mars, for example. If we put Betelgeuse or Antares in the center of the solar system where the sun is now, it would extend out past Mercury, Venus, Earth, and Mars, and its outer fringes would be in the asteroid belt almost out to the orbit of Jupiter, an enormous star. So those are the biggest ones. The sun, as we saw before, 860,000 miles, is kind of in the middle. It's not anywhere near the hundreds of millions, but it's respectable size, just under 1 million miles in diameter. The white dwarf stars, which were the smallest ones known when I joined the Astronomical Society, those were planetary in size. Some as small as the Earth, some like Neptune or so, big planets, but planetary in size, like tens of thousands of miles in diameter at most. Then, here's some new things. A neutron star. We'll see later on what leads to them and what they're like, but the main thing is that they're very small. They're only a few miles in diameter, like the size of Memphis. You can imagine what that's like for their density, because they contain most of the material that was in the star that led to them, and now they're scrunched down to the size of a medium-sized city. So those are the those were amazing when they first came out. But it wasn't too long before that was completely trumped, and that was with black holes, which had been theoretical. Now there's very strong evidence for it. As we'll see, by definition, you can't ever see one. So those of you who say seeing is believing and that's it, well, you don't have to believe in black holes. But if you do, they have no size at all. They're a theoretical mathematical point. They have no diameter whatsoever, yet still have a tremendous mass. And we'll get to those later. So that's the range of size of stars, from hundreds of millions of miles to no size at all. Okay, other miscellaneous facts about stars. Many of them are variable. Their light output fluctuates over a period of time, from hours to days to months to even years in some cases. There's a whole group of people who, I wouldn't say do nothing, but they specialize in observing variable stars and reporting their results to the Variable Star, American Association of Variable Star Observers. We have one of those members in our midst, our treasurer, Bill Wilson, who observes the sun practically every day. It's possible too in Memphis. The sun is a variable star. We'll get into that later on as well. There are several kinds of variable stars. One is the kind that's easiest to understand, is an eclipsing binary. You have a pair of stars side by side orbiting around each other. I can only do that so far, one way and then back the other. If you have the brighter one in front of the dimmer one, it's pretty bright. If they're side by side, that's maximum brightness. If you then have the dim one in front of the brighter one, then it goes down quite a bit in brightness. There's one of these in the constellation Perseus, Algol. You wonder if the ancients knew about this. We've had speculations on this before at our meetings, but Algol means the demon. And if they thought that this star was winking at them, they thought it might be the evil eye up there in the sky looking at them. So you kind of wonder if they knew there was something special about it. Another kind of star is the Cepheid variable, which pulsates in brightness over a period of a few hours to a few days to months in some cases. And we'll see later on that these are very useful in determining distances in astronomy. How do we know that something's a million light years away? Well, we'll see how the Cepheid variables are the key to that, the yardsticks of the universe. And then there are the long period giant stars that fluctuate over just about a year in their periods. And Mira, which is Latin for wonderful or marvelous, they had to know that there's something unusual about that. Well, of course they did. They're bound to notice that. It goes from as bright as the North Star down to dead invisibility over the period of the year. They're bound to have noticed that. So that's probably where its name came from. The names of stars are mostly Arabic in origin, or modified, corrupted Arabic. Deneb, in the tale of Cygnus the Swan, Deneb is an Arabic word for tail, and it's in a couple of constellations that are animals that have tails, have a Deneb or Denebula or Deneb Kaitos, the tail of the whale, is part of its name. Some are Latin, like Mara and Polaris. Those are ones that have Latin names, but most of them are Arabic. And then there's the old standby version, and that's to name all the constellations, or the stars in the constellation, in decreasing order of brightness following the Greek alphabet, alpha, beta, gamma, so on. And followed by the genitive name of the constellation. So rather than Alpha Cygnus, it'd be Alpha Cygni. And Castor, Beta Geminorum. So that's a standard way of naming stars. Brightness of stars. Everybody knows they're not all the same brightness. Of course, there are different reasons for that. Some of them are inherently brighter than others, and we'll get into that. Others are just closer, which makes them look brighter. And then there's always that combination. So we have many reasons for the brightness of stars, but we do know that the stars are named according to their magnitude. The brightest stars were intended to be first magnitude. When Hipparchus set up this scale, a century BC nearly, he called the brightest ones first magnitude. And the faintest ones you could see with the unaided eye are sixth magnitude. And if you divide that into equal steps and see how bright they actually are, each one's about 2.5 times as bright as the other. So a first magnitude star is about 2.5 times as bright as a second magnitude star. And a first magnitude star is about 100 times as bright as a sixth magnitude star. 2.5, not times 5, but 2.5 to the 5th power is how you would calculate that. It comes out very close to 100. So that's the magnitude scale. Now with telescopes you can see much fainter because they gather a lot more light than your eye does. Okay, I already mentioned that, 2.5. So brightest 100 times as bright as the dimmest. Now we know that there are a number of stars that are brighter than first magnitude. Well, counting backwards from first, we come to 0. So there are several 0th magnitude stars. And then there's 2 that are even a negative magnitude, one of which we can see from here, and that's Sirius, the brightest star in the sky. It's about magnitude minus 1.5 nearly. And then the planets, most of the planets are even brighter than that. Venus can get to about minus 4.3. And if you're driving to the meeting this evening looking over in the west, you probably saw Venus. Kind of looks like an airplane sitting there with its landing lights on. Yes, sir.
The brightness is not an inherent quality of the star, it's how bright it is to us.
Yes, exactly. We have other words for that, like luminosity or absolute magnitude when we're talking about how bright it really is, but how bright it appears in the sky is the apparent magnitude, and tonight it's just the magnitude. Okay. Yes, okay? Yes.
Is the magnitude of brightness of variable stars
Mm-hmm.
measured by their brightest side, or is it the ones usually in
Oh, that's a good question. You actually measure the whole curve and you put it on a graph and show the magnitude as it changes. It doesn't have a magnitude. It's variable. So you take that into account when you do it. It's a good question, but they don't try to give a short circuit result for that. Okay, star formation. To me, this is the most fascinating part of astronomy because you can see it all happening around you at any observing session. If those of you who picked up the schedule for our observing sessions, you'll see that we always start out with nearby things in the solar system. We look through the stages of stellar evolution, the various kinds of nebulae, clusters, and things, all the way up to the end of their lifetimes. We kind of take a tour of the universe like we're doing tonight, we plan those into the observing sessions. So star formation begins in dark nebulae, like the Horsehead Nebula in Orion, or the Coal Sack in the Southern Cross. These were used to be thought of as holes in the sky where there weren't any stars. But that's not the case. It's just an obscuring cloud in the foreground that keeps us from seeing stars through them to the background. So now we know what they are. Here's an example of the Horsehead Nebula in Orion, this little dark thing right here, and most of this dark area is rather cool gas and dust that's obscuring the light from stars behind it, or even this glowing nebula that's behind it as well. Let me just put in one word for astronomy here. Everybody who is in any kind of science thinks that what they're dealing with is really beautiful, right? Even if it's sea slugs or something like that, fungi. Well, in astronomy, we've got the real deal. Not only is it very intellectually stimulating and satisfying, but that's just plain pretty. There's no doubt about that. So we have some of the most gorgeous things to look at of any branch of science. So this is the Horsehead Nebula in Orion. By the way, all the photographs I'm showing you, except the very last one, are taken by amateur astronomers like us. These are not from observatories, but for people who roll out a telescope into their driveway and take exposures with CCD cameras and things. So these are all within reach of what you'll be able to do eventually. They're found in the spiral arms of the galaxies. You saw that drawing earlier. Well, here it is again. I thoughtfully put it back in again. These little pink areas here are these dark areas, are the dark nebulae that are in the spiral arms of the galaxies. They obscure the light from behind them, as we've already seen, and they're mostly hydrogen and helium with traces of the other elements. It's mostly hydrogen, a few percent helium, and about 2% of everything else. That's what the composition of these is, and we'll see how that came to be and what the ramifications of that are later on, like us, for example. And also, the temperature is extremely low, close to absolute zero, 273 below zero on the Celsius scale, or zero on the Kelvin scale. Not much molecular motion at all. Other examples that we'll see, dark lanes in the Lagoon Nebula, the Trifid, and Orion Nebula. Here's the Lagoon Nebula in Sagittarius, a summer object. See the dark lanes through there? Those are dark nebulae. Here's a good one in the Trifid Nebula. Not Trifid, by the way. That was a lower than grade B science fiction movie back in the 50s, the Day of the Triffids. That's not this. This Trifid means it's split into 3 parts. And the splitting stuff is dark nebulae. And here's the famous Orion Nebula, which you can easily see with the naked eye. It's on your star map, M42. We'll get into that later on. Here's the dark finger sticking in. Some people say that's the finger of God sticking in. Those of you who know me will know that I see the hand of God in all of the creation, but that's not it. This is just gas right there. Okay. They eventually evolve into emission nebulae. An emission nebula is one that's got hot enough to give off its own light. Now, how does that happen? Gravity compresses the dark nebula until it starts to get hot. If you ever pumped up a bicycle tire, you know that when you compress a gas, it heats up. And as it heats up, it eventually gets spots in it with more gravity than others where material is clumping together, and it starts to glow with its own light. And when it gets to that point, new stars or protostars start to form within the nebula, and they give off generally red light. Those are these spots, not this red light, but that. See all the little pink areas through there. You can see those on any clear night when the Milky Way is visible. Just set up a camera and open it up for 20 seconds or so, and see what comes up. You'll see little pink spots all along the Milky Way. Those are these nebulae with the glowing clouds of gas forming new stars. It's very easy to do these days. Frequently, you'll see the new stars embedded in a glowing nebula. And again, the Lagoon and Orion, we'll see right up in here. Those fuzzy-looking stars, those are fuzzy-looking because they're inside the cloud of gas, and they're causing it to heat up and give off the light. Same in the Orion Nebula. This is kind of an overexposed picture. It actually looks better through our telescopes. You can see more detail because your eye has a tremendous range of sensitivity, whereas film and even CCD doesn't. But inside here you can see a lot of detail that don't show up in the picture. Eventually, most of the gas and dust in the nebula gets used up forming the stars. And then the new stars, their light shines off of the remaining wisps of nebulosity, and we call that a reflection nebula, where you got a new star surrounded by little bits of the gas that it formed out of. And more examples, the Trifid again, and the Pleiades. This part of the Trifid is what we're talking about now, up here. You can see that's a brand new star, and it's a very hot blue one. It's relatively young, and even though you can't see its color because it's burnt into the film, you can see its light reflecting off the surrounding gas that's blue, and that tells us that it's a new star and it's a reflection nebula. Here's everybody's favorite reflection nebula, that's the Pleiades. It's hard to see the nebulosity within Memphis. You have to go way out in the dark area, and then you can see that light shining off of these. This is the Seven Sisters, the Pleiades. It's almost overhead these evenings. Some people think that's the Little Dipper, because it is kind of dipper shaped. Well, if you want to call it the Little Bitty Dipper, I suppose you could, but it's not the Little Dipper. And it's a star cluster and a reflection nebula all in one. Finally, all the traces of the nebula are gone. They're either used up making the stars or blown away by the heat and light from the stars. They're either incorporated into it or dispelled. And then all we have is a new star cluster. That's how star clusters are formed. And examples from this time of year here, the Beehive cluster in Cancer. There it is. It's on your star map. It's between constellation Gemini and Leo, where Jupiter is. So if you see Jupiter out there, which you can't possibly miss, it's the brightest thing in the sky, just go up from there with your binoculars and you'll run across this beautiful cluster of stars, the Beehive. And here's become my favorite since the Australia trip. This is one like it in the southern hemisphere in the constellation of the Southern Cross, the Kappa Crucis or jewel box cluster. Here's a globular cluster I was telling you about earlier that surround the nucleus of the galaxy with maybe 100,000. This one probably has about 500,000 stars in it. That's Rick's favorite to show off to people in the summertime. It's just a real crowd pleaser if you can keep the scouts or whatever from trying to count them once you tell them there are 100,000 in there. Okay, here's where we skip a whole lot of stuff. The new stars spend most of the rest of their lives converting hydrogen into helium and giving off energy. The same process that takes place in a hydrogen bomb, except under a controlled way, with the pressure and temperature balancing and the stars just chugging away, turning hydrogen into helium. When that process eventually stops, and it will for all stars, moderately small stars like the sun turn into red giants. They just expand. When that happens to the sun, it'll make things a whole lot different here. Mercury and Venus will wind up inside the sun, and it'll probably be kind of lapping at our doorstep, and probably the Earth will be glowing red like the sun itself then. Meanwhile, that rapid expansion causes the surface of the star to detach and float on out into space and form a shell around the star. and we call that a planetary nebula. And of course, that has nothing to do with planets. It doesn't have anything to do with their formation or anything. The early astronomers saw these little disks of gas and said, that looks like a planet. Because you know, when you look through a telescope, stars look like little tiny points of light. They have no size at all. They're so far away. Anything that looked like a disk back then was a planet until they discovered these planetary nebulae that were gas clouds. They knew they weren't planets because they stayed in the same place every night and didn't wander around like planets. So that was a new category of object in the 1700s, planetary nebula. Here's some examples of those. Here's, part of that example is the star that did it all usually stays there right in the middle and becomes a white dwarf star, you know, shrinks down to maybe the size of the Earth or maybe slightly larger. Okay, here's the Dumbbell Nebula in Vulpecula in the summer. Here's the cloud of this star right here. Used to be like the sun. Then it became a red giant, cast off the shell of gases, which is still expanding, and then it shrank back down to become the white dwarf star right there in the middle. And here's probably the most famous one of all, the Ring Nebula in the constellation Lyra, one of the showpieces of the summer sky, very easy to find. It's a little older because you can see the ring has completely moved away and left kind of a gap of empty space. It's three-dimensional. It isn't like a flat ring. It's a shell. And that's the star that did it all right there. Very large stars wind up with a more spectacular end. The blue giants, like Rigel or Spica, when they use up their hydrogen or the usable parts, they turn into red supergiants like Betelgeuse and Antares. So the next time you're looking at Orion in the sky, you find them on your sky map, look at Rigel and his heel, the blue giant star. Then look up at Betelgeuse and you can see what Rigel is eventually going to turn into. The blue giants turn into red supergiants after a while. Then, after they've used every trick in the book to stay alive, they suddenly collapse. And by suddenly, I mean in less than a day, just a few hours. They collapse and trigger a tremendous explosion known as a supernova. And then later on, you can see the remains of the smithereens of the star that has exploded as a supernova. And there are a couple of these I want to show you some pictures of. Sometimes the star in the middle, still there, gets scrunched down to become a neutron star. We'll go into that a lot more, sometimes even a black hole. But we'll see that those are the final stages of very big stars. And sometimes, you've probably heard of the term pulsar. All that is a neutron star that spins around very rapidly in just the right orientation so it looks like it's flickering. We'll go into that. I have a personal story to tell you about on that when we get to it. Here's the first one in Messier's catalog. Richard Townley will be talking about Messier after the break, and this was the one that started him on his career of listing things that weren't comets but might be mistaken for them. M1, the first one in his list, and this is the remains of a supernova that was recorded. It was observed in the year 1054, and ever since then it's been expanding, and you can figure that that's when it happened. The smaller of the two stars there in the center is the actual one. The other one's in the foreground. Here's one that's obviously much older. This is, you can't possibly sort out in here what was the star that did it, but you can see the remains of the outer shell of that star that blew itself to pieces probably 100,000 years ago. Okay, finally, let's see, where did we get? The neutron star, we already mentioned that. And sometimes neutron stars collapse still further to have no size at all and become a black hole. That's part of the story we'll get to in the summer, I think. Okay, finally, looking around our Milky Way galaxy, how does this all fit in? First of all, everything I've shown you so far has been within our galaxy. We haven't looked at anything else. We saw in our solar system and relatively nearby stars in our galaxy. Every picture you've seen so far is a Milky Way object. And it, as we said, it appears as a band of light going around the sky at night. And it's our ladybug view of from where we are inside the galaxy. At different times of the year, the nighttime side of the Earth faces different directions. In the summer, we face the nighttime side of the Earth faces in towards the center of the galaxy, and it looks brighter in the summer because we're looking in towards the hub of the wheel then. In the winter, the Earth's orbit takes it out to the outer edge of the galaxy, or out facing the outside of the galaxy, and we look out there and it's not nearly as bright through Orion and Gemini and so on. This, of course, is not to scale. This makes it look like the solar system is several thousand light years in diameter, but if I drew it to scale, you wouldn't be able to see it. So this is just showing how we see the inside of the galaxy in the summer, the outside in the winter. Any question about that as to why the Milky Way looks brighter in the summer than in the winter? Okay. That's on the test. So, you know. Okay. Okay, already said that. Here's a picture of that. The Milky Way going through Scorpius. There's Antares. There's the head of the scorpion. There's the tail of the scorpion. Here's the teapot of Sagittarius. And this beautiful picture over the lake there shows us looking right in towards the very center of the galaxy, where it's the brightest. We're not seeing individual stars there. All of those individual stars are close by. It's sort of like if you're out driving at night in the country and you see individual lights on by the road, or people have glare bombs on their houses to ward off evil spirits and so on. You see individual lights there. But then if you go over a hill and there's a town 20 miles down the road, you just see kind of a glow from that off in the distance, all the combined lights. That's what we're seeing here, is the combined light of all those stars in towards the center of the galaxy that we don't see as individual points of light. In the winter, we're looking out towards the outer rim of the galaxy, and here's a nice picture of that with Orion. That's Jupiter, by the way. When it was in Taurus a few years ago, there was Orion, Castor and Pollux in Gemini, Auriga the charioteer, and we can see the outer part of the Milky Way. It's still visible, but it's not nearly as bright as when we're looking in towards the middle. Okay, here's a startling fact. With our naked eyeballs, we can only see about 1,000 light years away from our solar system, out of the 100,000 in our galaxy. Any individual stars we see are really our next door neighbors. They really are, just the nearest ones. Beyond that, everything just blurs together. All the stars in the constellations, everything on these star maps are dozens or maybe hundreds of light years away at the most, not anywhere near the size of even our own galaxy. So we're only looking at about 1% of the distance across our galaxy, 1,000 light years out of 100,000. So we're looking at a tiny fraction. Here's our solar system, the whole thing, again, not to scale, but 1,000 light year radius out near our area, out near the outer edge, and then 100,000 all the way across. So this is where all the constellations are that we can see, is within that little circle. So we're just looking hardly down the road when we're looking at the sky at night. For a long time, astronomers called the Milky Way galaxy the galaxy, as if it were the only one. But they did know about some other things. They were little pinwheel-shaped fuzzy objects. John Herschel called them island universes. He kind of had a premonition as what they were. But they were called spiral nebulae, because they looked like little fuzzy spots in the shape of a spiral. Now we know that the spiral nebulae are actually other galaxies like the Milky Way, and that we're not the only one. The nearest big one is M31 in Andromeda, frequently called the Andromeda Galaxy, or just Andromeda. Andromeda is really a constellation, so that's not a good name for it. It's 2.5 million light years away. Notice how the numbers jumped then. 100,000 for our galaxy diameter, 2.5 million. That's 25 times farther than the size of our own galaxy to the nearest other galaxy. Here's a picture of it. Here's kind of maybe what the Milky Way looks like. It's a house across the street. Here's the big flat galaxy with the dust and gas and the nebulae and the star clusters around it. All these stars are Milky Way stars in the foreground, and we're looking out through them, between them, way beyond them. You know, these stars may be 1,000 light years away. This is 2.5 million light years away. And it has a couple of satellite galaxies. We'll get into that later on. So does our galaxy, by the way. But this is our nearest neighbor, big galaxy. There seem to be, the best estimate, nobody can count to 1 trillion, but we can estimate that there are probably about 1 trillion other galaxies in the universe. So we've come a long way since the invention of the telescope to being a member of the only, or the galaxy, to one of 1 trillion, and they're at distances of up to billions of light years. Now that has some interesting implications that we'll look at, but let's look at a couple of galaxies first. Here's one in the spring sky, M51. It's a double galaxy called the Whirlpool. You might be able to see another little one off in the distance right there. These are either merging or might have been formed that way. Might have been a collision. We don't know for sure. That's about 10 million light years away. This one's about 20. This is the Sombrero galaxy in Virgo. It might look like a Mexican hat, I'm not sure, but you can again see the dust and gas around the middle. It's easy to find. We look at it at our observing sessions then. Here's a cluster of galaxies, not a galactic cluster, but a cluster of galaxies. They're associated with each other. There's some kind of gravitational attraction holding that little group of them together. And here is the most distant one I'm going to show you tonight. This was taken with the wide field planetary camera of the Hubble telescope. One day, it was said to be on a Christmas day. They weren't using the telescope for anything, so they just aimed at a kind of a blank area in the sky and took a long exposure photograph. And when they looked at it later, this is what turned up. Do you see Milky Way stars in the foreground here? Well, there are actually 3 that I can see. That one, and there's one up here, and there's one more when I got a better vantage point. Oh yeah, right there, yeah. Okay, so we got maybe 3 Milky Way stars in this whole thing. Everything else in that picture is a galaxy. So when you use higher and higher magnification and look deeper and deeper into space, you start to see more galaxies than there are stars in our own galaxy. So we saw 100 billion stars in our galaxy, so this is where we kind of come up with the estimate of maybe 1 trillion other galaxies in space.
I'd like to ask, what the number's not clear, 1 to 200 billion galaxies?
Well, is that a new book?
No, actually, of course, just recently, and then I just looked up online. 1 to 200 billion galaxies.
Okay, that's a factor of 5 or 10 at the most. It could be. I'm not going to argue about that. No, but I mean, it could be 200 billion or it could be 1 trillion. Most of the information I have leans toward 1 trillion, because every time they get better telescopes and jack up the power, they start seeing more and more stuff in between where they thought the most distant ones were before. So it doesn't affect our picture of the universe as to how many there are. So pick a number. How about 600 million? Somewhere in between. Yes.
Looking back at that picture of the Hubble of all those galaxies.
Yes.
From our perspective, how big
A tiny fraction of a degree. You know,
outside 360 degrees?
well, more than that, spherical. 360 this way, 360 that. Was it 10,800 or something degrees in the sphere? Anyway, there's the moon is about 1/2 degree in diameter, and this is way smaller than that. They call it the wide field planetary camera, but this is actually a very narrow field of view that we're seeing. Yes?
Yeah, to clarify, if you imagine holding a grain of sand in your fingers at arm's length and looking through that grain of sand,
Mm-hmm.
that's essentially what we're looking at right there.
Okay. Very small area of the sky.
So it seems like a pretty big number.
I would say, yeah. Yeah. It's we'll get it more into that later on as this progresses, but like I said, the actual number is not a deal breaker on the fact that the universe is extremely large and has a lot of stuff in it. To finish up here, the time machine effect. I've alluded to this some already. We don't see anything in the sky as it is. Now that's unusual for science, isn't it? You look through a microscope, you see the little paramecium swimming around as it is right then. You pick up a leaf and you look at it, that's the way it is, not the way it was, it's the way it is. But in astronomy, everything is not the way it is. Now at first you might think that's inconvenient to have everything getting away from you like that. But actually when you think about it, it makes astronomy unique in that you can see the history of events by looking back different times, by looking back different distances. You can almost see the history of everything laid out in front of us because we don't see anything the way it is. So the moon, 1.3, the sun, distant planets, ours, nearest stars, years ago, far side of our galaxy, 80,000 years before, and other galaxies millions or billions of years ago. That lets us see how things are happening. And with the naked eye, we only see a small fraction of the universe. We see nothing as it is now. But despite all this, we've learned a whole lot in the last few hundred years, and I hope you've learned a little bit about that this evening, and we'll go into it in more depth as we proceed through the rest of the short course. And we hope that you will learn about the universe as well, and that you'll come back and tell your friends. So I'd like to thank you for your attention. Okay, we'll take a little break now between the presentations and pick up things that you haven't already, and we'll continue in about 10 minutes or so. Okay.